Okay, let's talk about planar kinetics and rigid bodies in translation. So say we have a rigid body here with the center of gravity maybe here, and this rigid body has a number of loads on it, forces. Let's make that a 2. And there can be moments on this thing. We can have a weight that we will center at the center of gravity. And we can get a resulting angular acceleration and angular velocity. So let's look at this whole thing from a fixed, with respect to a fixed reference frame, P. So P is fixed. And let's develop our equations of motion for translation. So for just translation occurring, we can get our equations of motion by equating the free body diagram with all our forces drawn. We can equate this free body diagram to our kinetic diagram then, which will include our accelerations and masses. So the inertial terms, mass times the acceleration in the x direction, and say mass times the acceleration in the y direction. From this, we can get our two mutually perpendicular expressions, summation of forces in the x direction equals mass times the acceleration in the x direction, and summation of forces in the y direction equals mass times the acceleration in the y direction. Now, for rotation, let's sum moments about P, because we could have applied moments, as was shown before. And we'll have another inertial term over here in our kinetic diagram, represented by I, alpha. And this would be I about the center of mass, alpha. So if we did that summation of moments about P, let's call this positive, then we're looking at the summation of R cross F, all our R cross F's, plus the summation of all of our moments. And then we would set that equal to R cross mass times the acceleration of G plus I G alpha. So in general, from this we can get three equations. We're looking at summations of forces in the x direction, again, equals the mass times the acceleration of g in the x direction. And again, the summation of forces in the y direction, mass times acceleration of g in the y direction. But additionally, we can choose another equation by summing about a point, say P. P is a stationary point here, the reference point of our, or the stationary point of our reference frame. And so we would then have to take the moments of our kinetic relationships about P2. And that means we would need moment arms. So a moment arm, for example, like this, that we could maybe say is an X bar moment arm, and this as a Y bar moment arm to these two vectors. So with translation, all particles have the same acceleration, and it's convenient for the equations of motion to take, of course we have our x and our y relationships, but it's convenient to sum moments around the centroid, because when you sum moments around the centroid, then y bar and x bar go to 0, and we lose this cross product term here. In addition to that, all particles have the same acceleration, and that acceleration is the acceleration of g. And since there's no rotation, we have alpha equal to 0. And that means the second term over here in our kinetic relationships also goes to 0. So we end up with these three equations, summing moments, if we sum moments about g. Now, we can sum moments about any point if we wanted to, like say for example point P or any other point other than the center of mass, if it might simplify our problems. And sometimes we do this if we want to eliminate the force in the equations. We could sum moments about a point where the line of action of the force goes through it, so it had no moment arm. And when we do that, say we have the body as pictured here experiencing rectilinear translation, so every particle in the body has the same acceleration in the direction of motion here. We would, so if we picked some point A to sum moments about, say it was here, because that will eliminate this force in our equations, in our equation that we're going to develop, then we would have a moment summed around that point there in our free body diagram. Then over here in the kinetic diagram, we have mass times acceleration of g along the line of action here. This d distance here is the d that's represented up here. We would have to take this into account, and that's only if, again, if we sum moments about a point that is not the center of mass. Now suppose now that our rigid body is translating still, but it's following a curvilinear path as it does so. Well, again, this might be loaded with forces. And moments. Certainly, possibly a weight here. But all of these will be with respect then to what we could define as a normal coordinate and a tangential coordinate. So if this is our free body diagram, this would be equal to, here we would have a mass times the tangential acceleration and this would really be the mass or the acceleration of g is what we'd look at tangentially, and then likewise mass times the acceleration of g normal. So we would now have, instead of x and y, we would have summation of forces normal and summation of forces tangent equals the appropriate inertial terms. Again, we could sum moments about g, and if we did that, there are no moment arms for our inertial terms over here, so this would equal 0. And we have no rotation or angular acceleration. This is following a curved path, but all the points, none of the points are rotating around g. So we could use that as our equations of motion, or we could also decide, instead of summation moments about g, we could sum moments about some other point, say b, and then this would not be equal to 0. Now we would have to, well, let's give this over here b, we'll call this a just because I drew it on there. So now we have to have an some distance e, say, and some distance d here. So we would end up with E times mass times acceleration of g tangential plus D times mass times acceleration of g normal. And I redrew these so that they were in the correct directions. And you might want to do that again if, for example, you want to eliminate a force over here. You might want to take a moment about a point that force goes through. You could eliminate maybe a number of forces where they intersect. You could use that point potentially to quickly and easily make your problem a little simpler.